let us proceed with lecture 13. Topics to be covered for lecture 13 will be boundary conditions for today's lecture. We're going to continue on capacitance in our class this coming Thursday. Yeah. So reference for these topics can be obtained from these pages of StudyCool. Yeah. So if you have enough time or extra time, please have a look at these references for more information. Yeah. Okay. So objective for this lecture number 13 basically is to understand the concept of boundary conditions. Okay, so that should be the main objective for topics number 1, which is boundary condition. And number 2, this will be learned later on Thursday. Yeah? So I'm going to cover this objective. Okay, so let's have a look at the boundary conditions topic. So boundary conditions basically is to find the value of the physical parameters at certain boundary. For instance, based on what we have here, I'm using the heat as our physical parameters. So let's say we have a heater here, yeah, and we have a conductor, and the ambient material is the air, which is at 27 degrees Celsius. So basically, we can see that the heat, yeah, the heater will produce a heat in which it will flow in your conductor's material. And in order for us to find the value of temperature at this boundary, boundary between the conductors and the air, yeah, we need to use what we call as boundary conditions. Yeah, boundary conditions shall be requested or shall be required in order for us to calculate the temperature at the boundary between the conductors and the air or the ambient. Yeah, so that is the importance of boundary conditions, which enable us to calculate the value of the physical parameters at the boundary between two materials. Yeah, between two materials. Okay. So in our case, because in our study of electric field intensity or electromagnetic theory (EMT), our physical parameters is electric field. Yeah. For this case, it's a heat. Yeah, it's temperature, to find the temperature. But for our case, is to find the value of electric field intensity E. So E field intensity is our physical parameters. So that should be our aim, in which if we have two materials, for instance, yeah, if we have a material between conductors and free space, for instance, this is a free space, this is a conductor material, okay, conductor material. So we have a boundary between the free space and conductor. What should be the value of electric field intensity that will be produced at this particular boundary between these two materials of free space and conductor? Okay, yeah. So hopefully you have understand now the importance of calculating or knowing the value of electric field intensity between two mediums. Yeah. So in our case, since we have learned a few mediums up to now, where we have a free space, we have learned about the conductors, we also learned about the dielectrics. So basically, the boundary conditions will be investigated for 3 different cases. The first one will be conductor to free space boundary condition. Secondly, will be on conductor and dielectric boundary condition. And finally, will be on the dielectrics and dielectrics boundary condition. So 3 main boundary conditions will be covered in this lecture number 13. Yeah, so I repeat again, the importance of boundary conditions in our case here in EMT is to calculate, is to know what is the value of electric field intensity at the boundary between two medium. Yeah, if you base on this diagram here, if you have a free space and conductor medium which is in contact, which are in contact with one another, yeah, so basically that should be the boundary between the two medium. So we can use the boundary condition equation to find the electric field at the boundary between the two mediums. Yeah, the same things apply if you have a medium between a conductor and dielectrics, a medium between dielectric and dielectric. So that's why we have 3 different mediums or 3 different boundary conditions to be investigated for this particular case of boundary conditions. Yeah. Okay, so let's have a look at the boundary conditions for the first case, which is for the conductor and free space. Yeah, conductor and free space. So we're going to formulate the equations for boundary conditions. Yeah, okay, this is the case whereby we have a conductor, we have a free space. So you want to find out what is the resultant electric field at the conductor and free space boundaries when we apply the external electric field to these combination of the mediums of free space and conductor. Okay, so that should be the graphical representation that we can use in order to study the boundary conditions between the free space and conductor. Okay, we use the upper boundary. Okay, so we have a medium number 1, which is a free space medium, and number 2 medium is a conductor. Based on this diagram, we have agreed that the upper will be the free space and the lower part will be the conductor. Okay, and we assume that on the surface of the conductor there is a charge of rho s, which is agreeable to what we have learned previously when the conductor is applied with the electric field. We have learned that when the conductor is applied with the electric field, the rho s, the surface charge density, will be produced on the surface of the conductor. So the assumption of having a rho s on the surface of conductor here is valid assumption. Right, so that should be the case. So now we're going to have these conditions. Electric field will be propagated in your medium, following this electric field direction. So E2 is the electric field in medium number 2 in the conductor. E1 is the electric field in medium number 1, which is in free space. So basically, in order for us to find the boundary conditions or electric field at the boundary between the free space and the conductor, we need to actually obtain relationship between the E2 and the E1. So that is the first thing that we need to obtain. We need to find relationship between the E2 and E1 so that we can find what should be the value of electric field at this particular boundary between the free space and conductor. So to find relationship between the E1 and E2, what we have to do is that we have to separate both E1 and E2 into their respective normal and tangential components of the electric field. Okay, so that's why we have these separation of both E1 and E2. Okay, where we have the E1 is separated into normal inner vector E1n and E1t, which is a tangential inner vector, tangential component of the electric field. And the same thing is applied for the E2, where we have separated the E2 into E2n, which is normal inner vector for the E2, and normal electric field for the E2, and E2t, which is a normal electric field for the E2. So we have E2n normal and E2t, which is the tangential components. So that should be the step that we have followed so far. We have separate both E1 and E2 into their respective normal and tangential components. Okay, so our next task is to find relationship between the E1 and E2n, and then we need to find relationship between the E1t and the E2t. So we're going to have two different conditions to be analyzed now. The first one is to analyze the normal component, and the second is to analyze the tangential component of these electric field 1 and electric field number 2. Okay, so let us proceed with the analysis of the normal component first. Okay, so we just consider normal components for this diagram. Just to recall back, this is a free space environment. This is your conductor medium, conductor material, and rho s is the surface charge densities on the surface of your conductor. So we need to find what is relationship between the E1n and the E2n. So for this particular case, we can use the Gauss Law, to find relationship between the E1n and the E2n. So what we did here is we sketched the Gauss Law. So this dotted line, cylindrical structure, is your Gaussian surface. So if we can write the Gauss Law equation for this surface, that should be surface number 1. Down here should be surface number 2, and the curved surface should be surface number 3. Okay, so let us proceed with the Gauss Law. So we have d dot ds equals to enclosed charge. Okay, so if we base on the closed surface structure here, we have 3 surfaces. Surface number 1, 2, and 3. So we separate this integration into 3 different integrations. Surface number 1, of d dot ds plus surface number 2 okay. Okay, surface number 2 of d dot ds, okay, d dot ds for surface number 2, okay, and then we have for surface number 3, okay, which is also a d dot ds. Sorry for this interruption, yeah. Okay, whereas the Q enclosed is a charge which is enclosed by the Gaussian surface. Right, so remember that we have a rho s, yeah, rho s on the boundary of your structure here. So we can see that there should be a area which is bounded by this particular Gaussian surface. So we can see that the Q enclosed should be written by integration of rho s. Yes, yeah, that should be the amount of charge that will be enclosed by the Gaussian surface. Yeah. Okay, so if I put, or if I just take that the cross section of this structure is a delta S, yeah, the cross section of your structure is a delta S, I can write that for surface number 1, yeah, for surface number 1, I'm going to have the equation here as equals to d1n multiplied with ds positive. Okay, that should be my d dot ds for surface number 1. Whereas for my surface number 2, for surface number 2, I'm going to have the d dot ds to be d1n, sorry, d2n, I apologize, d2n, and then we have a negative for delta s, yeah, negative of delta s, yeah, because the d dot d2n is in the positive direction, while delta s basically should be in the negative direction, so we have negative delta s for that, yeah. Okay, and for the third surface, yeah, we know that for the third surface, which is a curved surface there, the d vector is in the vertical direction. Yeah, that should be the d vector, vertical direction, but the ds is in the perpendicular direction. Yeah, so that's why the d dot ds for the third surface will give us 0. Yeah, so d dot ds for the third surface will be 0 due to the reason that d and ds in a vector for third surface are perpendicular between one another. Yeah, means that the d and ds, both of them are perpendicular, and as such, the value for dot product will be 0. Yeah. Okay, and from this equation, we can write straight away that for number 1, yeah, for surface number 1, the equation will be written as d1n delta s. Yeah, delta s should be there. Minus d2n of delta s. Okay, and then we are having the equation here as rho s of delta s. Yeah, because we have agreed that the cross section of this Gaussian surface is delta s, so we simply write this as delta s. Yeah. Okay, but as what we have learned before, yeah, remember that this medium E to N is a conductor. Yeah, conductor is mean number 2, and we have agreed from previous lecture 10 that in conductor electric field will be 0. Yeah, electric field in your conductor will be 0. So as such, we can see that due to this understanding that the E in the conductor will be 0, we can see that the D to N will also be 0. Yeah, because we know that the D is equals to epsilon naught of E field. Yeah, so when E is 0 in your conductor, the D will also be 0. So that's why we can write that for this equation, yeah, initially we have D1N delta S minus D2N delta S equals to rho S of delta S. But knowing that the D to N will be 0 as a result of this understanding of this condition in your conductor, so I have simplified the equation to be only D1N delta S equals to rho S delta S. So delta S and delta S will be cancelled out. So we have equation of D1N equals to rho S. And as such, we can write that the E1N should be equals to rho S over epsilon naught from relationship of D1N equals to epsilon naught of E1N. Yeah, that's why we have the E1N should be equals to rho S over epsilon naught, in which E1N here is the electric field in your free space medium. Yeah, so that should be the electric field that will be produced at the boundary between the conductor and free space. Yeah, which means that when the conductor and free space are said to be in contact with one another, we can say that the electric field only exists on this free space medium, in which you're going to have the E1N value equals to rho s over epsilon naught. Okay, let's have a look at the tangential components. Okay, so for the tangent components, to find a relationship between the E1T and the E2T, yeah, we can use this relationship, which is the equation for the second law of Maxwell, yeah, where we have the closed loop integration of E dot dl equals to 0, work around a closed loop equal to 0. Yeah, this is the equation from the second law of Maxwell. Okay, so we can have from E dot dl equal to 0. Yeah, based on this diagram, we can have that this closed loop integration shall be written as integration from A to B of E1T dot dl plus integration from B to C of E dot dl. Sorry. Yeah, because from B to C we have two combination or contribution of E field, which is from E1T and also from E2T. So I just put it in general to be just E. Okay, and then we have from C to D, we have E to T dot dl. Then we have from D to A of E dot dl equals to 0. Okay, so if we base on this integration, we can see that from B to C and D to A, the value of E dot dl will be 0, yeah? B to C and E dot dl, D to A will be 0. Because why? Because we have learned from this diagram that from B to C and D to A, the dl is in vertically directed, yeah, a vertical direction, yeah, vertical direction for the dl, but the E field is in horizontal direction. So since the E and dl, both of them are perpendicular for B to C and D to A path, so we can say that the E dot dl for both path B and C and D and A, B to C and D to A will be 0. Okay, so that will be 0 lah, yeah, from B to C and D to A as a result of E and dl, both of them are perpendicular. Whereas from C to D, yeah, C to D, we have learned that the E field will be 0 in conductor, yeah, because we know that number 2 is a conductor, and in conductor the E is 0. So because E is 0 in conductor, E to T will also be 0 in conductor. So as such, we only have a single terms of integration, which is E1T dot dl equal to 0. Yeah, E1T dot dl equals to 0 from A to B. Okay, so knowing this, we can say that the E1T can be simply written as 0 only, straight away. Okay, yeah, so now we have two terms for the E field, the E1N, the E1T, and we can then produce that from the previous slide. Yeah, so this is your free space, this is your conductor material. So we have agreed that electric field in the conductor will be 0. So in free space environment, as what we have learned before, we have two electric field terms, which is the E1T and the E1N. But we have agreed from the previous slide that E1T will be 0. Yeah, this is 0 because of these conditions that we have seen just now. And we are left only with the normal unit vector, in which normal unit vector, the E1N is given by this equation here. Yeah, based on the normal relationship just now, that the E1, which is the electric field in your free space environment, will be given by rho s over epsilon naught normal unit vector only. Yeah, so which means that if we have a boundary between the conductor and free space, the electric field will only exist in free space environment only. Yeah, we exist only in the free space environment, whereas the electric field value is given by this magnitude, rho s over epsilon naught, and the direction of the electric field is normal with regard to the surface of the conductor. Yeah. So if I can re-sketch this diagram, a conductor is here, a free space environment is here. So your electric field will be only in this direction, which is normal with regard to the surface of your conductor. So that's why I mentioned here that if we have conductor and free space boundary, electric field will always normal direction from the conductor surface, yeah, normal direction from the conductor surface, which follows this equation. Yeah, which follows this equation. E field will be rho s over epsilon naught, normal in the vertical direction. Remember what is rho s? Rho s is the surface charge densities which is located on the surface of your conductor. Okay.